All right, so in this video we're going to be looking to see how we can use synthetic division to help us factor a polynomial. But before we do that, we need to learn about some other theorems. One is the remainder theorem that says that if a polynomial, call that p of x, so if a polynomial is divided by a linear polynomial like x minus c, then the remainder is p of c. So we'll make sense of that here in a little bit. And the flip side of that is if the remainder is 0, then we know that x minus c is a factor. So let's look at this first example. It's asking us, is x minus 2, is that a factor of the polynomial? Well, how can we tell? We can use a factor theorem because, again, if the remainder is 0, then x minus c is a factor. And we can use the remainder theorem as well, because if we put c into the function, whatever you get as your answer, that'll help us also see if it's a factor. So we're going to use these two together. Okay, so the idea here is I'm going to use the 0. The 0 for x minus 2 is just 2. So in this case, c would be 2. So we're going to put 2, get my pencil ready here. We're going to put 2 in the function. So every time we see an x, we're going to replace that x with 2. And our goal is to see, well, if we plug that in your calculators, do you get 0 as your answer? And I would recommend not simplifying it step by step. I would just recommend plugging this in exactly as we see it, even with the parentheses, in your calculator, and when you do that, you get 0 as your answer. So what that tells us is that the original x minus 2, it is a factor of the polynomial. So what we're going to do is we're going to use that fact to factor this original polynomial. Because here's what we know now. We know that x minus 2 is a factor of that polynomial, so that means that x minus 2 times something else would give us the original polynomial. So to figure out what that would be, we can use synthetic division. So remember the 0 here is 2. And when we look at the original polynomial, we have a 3, a 2, and then 1, and then none. So everything's represented here, so we don't need to fill a position with a 0. So we're going to start with the coefficients, 1, 2, -5, and -6. Draw our line, enter box. So I want you guys to use synthetic division on your own. You know how to do this now. So I want you guys to pause the video and hit play when you're ready to check to see if you've done it correctly. So let's see how you did. So you should have gotten as your answer the numbers 1, 4, 3, and then a 0 as a remainder. So the 3 would be your constant. We put an x then in the next term and then an x squared in the other one. So what that means is that x squared plus 4x plus 3, that times x minus 2 would give us the original polynomial. So we want to make sure that we factor this completely. So we know one of the factors is x minus 2, so we want to figure out is, can x squared plus 4x plus 3, can that be factored further? Well, remember, this is a value of 1. So remember what we've learned. We have all these tools in our toolbox. And one of those is for factoring. And when a is 1, we can check to see if it factors by seeing are there two values that multiply together to be 3, that add together to be 4, and sure enough there are. 1 and 3. 1 times 3 is 3, and 1 plus 3 is 4. So now this is the factored form of that original polynomial, which is what we see on the next slide. Okay, we already have that. I decided to do it all at once, so I'm just going to rewrite this. So we had x plus 1 and x plus 3. All right. So now let's list out the zeros. The zeros would be 2, -1, and -3. So we're going to graph this. So on your notes, you can you have a spot on your note page where you can sketch a graph. So just go ahead and draw an XY axis here. And the reason why I know it's going to look like this is we can easily figure out what the y-intercept would be. To find the y-intercept, remember that's where x is 0 and y is some number. So I could put 0 in. It's in a different color so you can see what I'm talking about. Every time we have an x in that factored form, we can replace it with 0. So if we do that, we would have 0 minus 2 is -2. 0 plus 1 is 1. 0 plus 3 would be 3. If I simplify that, -2 times 1 is -2 times 3 is -6. So we're going to have a y-intercept where y is -6. So let's go ahead and graph this out. So I'm going to put some dash marks up here on the x-axis. So I'm on my y. All right. So let's plot all these points. So we have an x-intercept of 2. We have an x-intercept of -1 and an x-intercept of -3. We know the y-intercept is at -6. 1, 2, 3, 4, 5, 6. All right, we want to make sure that our end behavior is correct. So before we do anything else, we want to go and figure out our end behavior. So remember, we have this parent function. It's down here at the bottom. So the end behavior, remember I talked about doing the 2 blanks. The leading term is positive, so the right side's going up. The degree is odd, so the left side's going to go down. So we're going to go up and to the right, down and to the left, and then connect these. All of these also have a degree of 1. So that means that all of those have an odd multiplicity, so it's going to be all pass-throughs. So there's not going to be any bounces at any of those x-intercepts. So this would be the shape of our polynomial if we were to graph it.